So thank you very much for the introduction. I also wanted to thank the organizers for putting together this workshop, although they're not probably here yet. All right, so today I want to talk about some work that we did in collaboration with people from MPQ in Munich while I was a postdoc there. So this is Ignacio Cirac and Yorgos Stileris, who is still a postdoc there. Right, so the common theme of this work, similarly to some of the talks we've seen so far, is to try to see how measurements enhance the possibilities of unitary dynamics in a many-body context. So this is going to be a talk about a single work, but since we touched upon a few topics, let me give you an informal summary of what we do here. So here we mainly do three things. So first we introduce a set of transformations which combine two natural objects, which are quantum circuits and local operations and classical communication, so LOCC. And then we discuss the power of these transformations in two specific contexts. One is state preparation, and the other is implementation of unitary operations. And then finally, there is a more speculative part, which is about suggesting a classification of phases based on this new class. All right, so there are clearly two main actors here, quantum circuit and LOCC. So let me start by introducing the first one. And I think it is convenient to do so in the many-body setting, starting from something which feels a bit unrelated, which is the concept of causality. So it's well known that in quantum mechanics, there is no built-in notion of causality, but there is a well-defined emergent notion of causality if one specifies the setting well enough. And here, the setting which I have in mind is the typical setting we have in many-body physics. So we have a well-defined geometry, which is some notion of distance. So this could be, for example, a lattice and some dimensionality, or more generally, a simple graph. And then we have a local Hamiltonian, which is a sum over your space of some local density Hamiltonian. Now, in this setting, the causality of the evolution manifests itself in the so-called Lieb-Robinson bound, which is expressed here. Essentially, it tells you that if you time evolve in the Heisenberg picture one operator at one point, it will essentially commute with another very far away up to a time which is essentially proportional to their distance. So this is the statement, and there is a probably more intuitive way of seeing this, which is about operator support. So suppose that now you are in one spatial dimension, so you have your line of qubits with a natural notion of distance. And then the claim is that if you have a local Hamiltonian dynamics and you time evolve a operator localized at some point here, then after a finite time, you will have that your operator is spread over a finite region up to some exponentially decaying tails. And so the kind of finite depth quantum circuits that I have in mind can be considered as the simplest discrete unitary operation, which has this form of strict causality as a built-in feature. So let me be more explicit. So this is an example in one dimension. So what I will call a quantum circuit is actually a finite depth local quantum circuit. And we can define these objects as a finite number of layers, and each layer is going to be the product of commuting gates acting on neighboring sides. And once again, it's crucial that we have an underlying notion of geometry, so an underlying notion of locality. So this is just a picture, and I'm not restricting myself to any universal gate set, so this can be whatever. And even if we do not restrict the choice of this use, it's very easy to see that we have this emergent notion of causality in a graphical way. So suppose, again, you start with your local operator at site J, and then you sandwich with respect to a depth2 quantum circuit, then you see that if you are sufficiently far away from this point, you will have some cancellations. And so at the end, you went from having a local observer localized at some point J to something which is spread over a finite region. And so this locality of quantum circuits is also consistent and say natural from the point of view of digital simulation, as you can show that this kind of local quantum circuit efficiently approximate a local Hamiltonian dynamics for a finite time. Okay, so this is one way in which quantum circuits enter the many-body business, which has to do with dynamics, but there is another one which is very natural and pertains to the classification of phases. So so this has been mentioned already many times, but let me state it once again for self-consistency. So in the traditional problem of classifying pieces of matter, what we have is ground states of local Hamiltonians, and then we want to know whether they're in the same phase. And by this, I mean that if we imagine that the two are ground states of two local Hamiltonian, H0 and H1, we can say that they're in the same phase if there exists a continuous path of local Hamiltonians which smoothly interpolate between the two. And so when this happens, it has been proven by Hastings that you can, in fact, directly jump from one to the other with some quasi-local transformation U. Because of the quasi-locality nature of this transformation, you can actually approximate it with some shallow quantum circuits. So put differently, this could be rephrased colloquially into a definition of phases, which is entirely in terms of this class of local quantum circuits. And we can say that two states are in the same topological phase if and only if they are connected by a low-depth quantum circuit. And here I'm using low-depth in a vague way. I'll come back to it later. Okay, so these are two aspects which are physical motivated, so the Lieb-Robinson bound and the topological classifications, which tells you that although this is a very natural class of operations, it's in fact limited fundamentally in the class of states that we can prepare. Because if you start with some trivial product state, we imagine some preparation protocols as those we want to implement in our devices, and we apply this kind of locally connected quantum circuits, then whatever we construct by the Lieb-Robinson bound is going to have short-range correlations, and sort of by definition of phases is going to be in a trivial topological phase. All right, so these are a very general principle, but they can be turned into very simple but precise statements. Let me just give you an example. So this is the extremely simple state, the GHZ state. So you have a chain of n qubits, and then you take the superposition. And now what you can do is an elementary calculation is to compute the two-point correlation function of the Pauli matrices. And you will see that this correlation does not factorize. So it's not true that the correlation factorizes. And it's a one-line proof using this strictly Lieb-Robinson bound that if you prepare the state with a finite depth quantum circuit, then this should happen. And so this simply tells you that there's no finite depth quantum circuit that can realize the state, although the state is a trivial state. And in using a slightly more elaborate argument, you can in fact show that all topological states, like the toric code, are out of the reach of these finite depth circuits. Okay, so this again provides a fundamental limitation, but let me stress that so nowadays topological order states have been constructed in superconductive qubits. There are these very nice papers here from people in the audience, and of course here I'm making a statement about scalability and asymptotic systems. So here, of course, they prepare, for example, in the first one, they prepared toric code in a relatively small number system with a small number of qubits, so there is no contradiction. All right, so then our goal here is to also motivated by how measurements have a bit revolutionized quantum dynamics, studies on quantum dynamics in many-body systems, to see how we can use these measurements to enhance our abilities to create and prepare states and unitaries. And so it's obvious that you need to break either unitarity or locality, and so we were looking for a minimal way to do so, and for many reasons, one natural way to do so is by means of LOCC operations, local operations and classical communications. So this is an extremely important class of operations in quantum information, which in fact you can see as defining the notion of entanglement itself. And let me just give you, I mean, this is something which has been studied for decades. Let me just give you one slide introduction to it. So these operations are thought to be defined in systems where you have no notions of locality, but only a notion of parties. So here, for example, you have three parties, and you would consider LOCC operations any transformation of your state defined on these three qubits, which involve local interactions with ancillas, some local measurements, and then some classical communication between parties. And then you're allowed to repeat. And then depending on how many rounds you do, this may define different types of LOCC operations, but this is, in essence, is what LOCC are. Okay, so the classification of states using LOCC is something which has been studied to death in quantum information because, again, people are interested to know how much entanglement as a resource we have in states. But a very natural, we think, idea is to try to combine QCC and LOCC to see now what the classification looks like. And this is also natural from the point of view of devices because this is something we can implement now in the lab. We can act with unitary gates, we can perform measurements, and of course then we can look at the outcome and do some classical processing of the information. Now I want to stress that there are many ways in which you can combine quantum circuits and LOCC, and depending on how you do it, you can end up with a trivial problem. So we have to be careful in how we define this class. So let me give you a graphical explanation. So what we do, we start with our lattice. Again, it's very important that we have some geometry. And then what we do is we allow for finitely many ancillas per site. So here, for example, we have the physical qubits, and we attach two ancillas to each qubit. And then we perform a finite depth quantum circuit. At the end of this, we apply a LOCC scheme. And there are two important comments. So first, the finite number of ancillas per site could be lifted, but then you have to restrict a bit the geometry of the circuits. But more importantly, we have at least two ways in which we can meaningfully apply these LOCC operations, and it pertains on how you do the measurements. One, which is very natural, is to measuring all the ancillas at the same time, and then doing some classical communication and processing of this data, or you could do some sequential measuring and operation. So everything I will say in this talk pertains to the parallel measurement. So we will always measure everything at the same time. And this is a bit more natural in times of, time of preparation. And I will not touch upon the sequential scheme, but I just wanted to mention that even in one dimension, there are very simple states which appear to be difficult to realize, or maybe impossible to realize with parallel measurement, but are trivial to realize with sequential measurement. So maybe I can come back to it later. Okay, so the two claims then is that this class, which is it's fairly simple, already allows to prepare more states than simply quantum circuits, but in fact to prepare unitary operations that would have required a very large, a very deep quantum circuit. Now, before giving a very simple example, let me stress why this problem is not trivialized by measurement-based quantum computing, and not even for Clifford states. So suppose that I want to prepare some one-dimensional quantum state within the framework of measurement-based quantum computing. So what I would do is I would prepare a 2D cluster state, and then I would interpret this as my trivial initial product state, and then I would proceed by measuring some of the qubits in this grid, adaptive measurements, and then at the end, so I will interpret each line as a time step. At the end, I will read the prepared state in the output of this tower. So for stabilized states, in fact, I can perform all these measurements simultaneously, and so apparently this trivializes the protocol, and it seems like I can create any state in this way. But the point is that this does not respect the geometry that we ask for, because if we interpret this, so imagine we want to prepare a one-dimensional system, we want a one-dimensional system to begin with. So here, if we want to interpret this 2D cluster state as a one-dimensional system, we would have these as physical qubits, and then we would need to interpret these as ancillary qubits. But then, so first of all, here the number of ancillas per site generally grows linearly, but another way to see that this is not, is outside the scheme that we propose, is that now if you bipartite this, again, as a one-dimensional system, this in general will display a volume law entanglement, and it cannot be realized with a finite depth quantum circuit. Okay, so now let me give you one slide just to as a very simple example. So let me come back to this GHZ state and give you a trivial protocol to prepare it with the scheme. So here, the construction of the state using this kind of adaptive measurement scheme is well known. There are many ways to do it, but this is just to show that there is a trivial way to do so. So here, what we do is we initialize our system with zeros in the physical system. We append one ancillus per side. Here, we don't append anything. And then we act on the system with a finite depth quantum circuit. First, we prepare bell pairs between one qubit and the neighboring ancilla. And then we perform some C0 coupling each qubit with its ancilla. So the state that we get then is this one. This is simply the wave function in real space. And then finally, we measure the ancillas in the computational basis. Now, here, of course, the state that we will get is a random state, which depends on the outcome of the measurement. But the point is that we can then use this information to act on the system and recover the GHZ state that we want. The way to do it is very simple. We act with local operation here, which is a product of unitaries, and the unitaries are written here. So you see it's a Pauli matrices exponentiated to some powers, which is the sum of the outcomes that you get. Okay, so here it's trivial, but it gives you a complete picture of what we're doing. Because first, we're clearly breaking unitarity by performing the measurements. But second, we are also violating, in some sense, locality, because if you, I mean, the unitary that you apply at site J depends on the outcome of all the other sites. So it's necessary that we also have non-local classical communication. And finally, this also shows you clearly in what sense we want deterministic transformation. So we want something that it's not random. So we want something that with probability 1 generates the state that we want. All right, so this is for the GHZ state and a construction, which again is very simple and in fact very similar, works, for example, for the toric code. This is something which has been already mentioned, and it was something that has been known for a long time. So if anything here, we simply pointed out that the scheme, so previous construction fall under the scheme. And just as a technical note, the reason why it's so simple to generate a toric code, I mean, the idea is that, as has been said before in previous talks, is that we measure all the stabilizers, we'll get some syndrome, and then we locally correct the syndrome with some unitaries. But the crucial point is that we can do this in the toric code because these anions can be corrected with local unitary operation. So this is really LOCC. So we do a measurement, and then locally we correct it. But this very simple scheme does not work for non-abelian topological order. And this is why when we first put this detector out, we were not sure whether non-abelian topological order could be addressed at all. But after that, as I will touch upon later, has been expanded upon significantly in works from other groups. Okay, so this is just to say that there are states which still we're not sure whether we can prepare. But there are states we are sure you cannot prepare with the scheme, and the reason is simply because we have an area law characterization of these states. So the reason why we have an area law, again, it's follows from known results in quantum information. So I mean, thinking of how we prepare the states, we take some trivial state, we apply a finite depth quantum circuit, and then we perform LOCC, and none of these operations can violate the area law. The only part which is maybe a bit tricky is about LOCC, but this is a result by Nielsen that when you have a LOCC which implements a deterministic transformation, bipartite entanglement cannot increase. Okay, so this set of transformations, the corrections that we've seen in the GHZ state depends very much on the state. Meaning that if I apply the same protocol, but you change the state, and I don't know that you changed the state, this is not going to end up in a pure state. Typically, it's going to end up in a mixed state. So then the next natural question is, okay, so you prepared, you have a way to speed up state preparation with your shallow quantum circuits. But the question is there a way to now prepare unitaries or unitary operations using shallow circuits and LOCC? So one example, which again, it's trivial, is this UGHZ. So it's a unitary which implements your GHZ state. And it's a bit frustrating that this unitary is extremely simple, but yet it takes a linear time in the system size to prepare it if you only have local gates. So the construction now gets a bit technical, but let me just give you the idea of why this is possible in some cases. And the idea is based on the concept of the choice state. So the trick here is to first realize a protocol that constructs a choice state, which is defined here. So for given a unitary operation, one construction which is well known in quantum information is to map your unitary into a state by doubling the degrees of freedom. And this construction has a corresponding physical process that in principle you could apply in the lab, which is the following. So suppose that you have your physical system. What you do to create really physically this choice state is to append one ancilla per site and then generate bell pairs between your qubit system and the ancillary system. And then you act with your unitary on the physical system. And this is a physical representation of your choice state. Now, suppose that someone comes and gives you the choice state of some unitaries. The claim is that, the thing that you would like to do now is to apply this unitary on the given state. And this would be very easy if you were allowed to do post-selection, because the way that you would do it is, okay, I have my choice state, someone gives me this psi state, and then what I do is I do projective measurements, Bell projective measurements, coupling AA prime, and it's a simple exercise to show that the output state now will be your U applied to your state. Okay, so what we aim for is to go through all the steps of this process, but again, using shallow quantum circuits, LOCC, and obtaining a deterministic result. Okay, so of course, you can already expect that the U's that you can prepare in this way is special, but already a non-trivial question for us is just how special should they be? What we can do is to find at least one class of unitaries which we can prepare, and the class is the following. So imagine that you start with some stabilizer state which you can prepare now using this QCC operation. What we can do is to engineer a unitary out of this, which prepares the state starting from a product state. Okay, so just for the expert, the idea is the following. So we use the fact that a stabilizer state is locally maximally entanglable, which means that you can always couple it locally to some ancillas, and by using local unitaries, you can create a maximally entangled state between system and ancillas. And then you can show that you can choose this in such a way that the resulting state is a choice state of a Clifford unitary operation. And so then you can simply apply your natural measurement-based scheme to obtain your unitary. So let me give you two examples. So one I already show is this UGZ state. And this can be obtained by first preparing your GZ state as I showed, and then applying this procedure to obtain this. Again, let me stress that the difference with what we did before is that this simple procedure is guaranteed to apply this operator now to any state, and it's not fine-tuned to the initial state that you have. And second, another unitary that we can prepare, because the toric code is a stabilizer state, we can prepare a unitary which, if you apply to a product state, generates the toric code. Again, here the message is that we can do this with shallow circuits, whereas in principle this unitary, and in fact this unitary, we know that should be, you can only prepare it unitarily with a very deep quantum circuit. Okay, so now let me come to the more the part which contains more speculations of our work, which is about now trying to use the set of operations to extend the classification of phases. Okay, so here what I want to do is now to take a more theoretical point of view. So we consider states in the thermodynamic limit which are translation invariant, and of course this introduces some subtleties which you can resolve in some ways. But what we can think of is that now we have sequences of system of increasing system size, and what we want to do is to define a equivalence relation in this class. So again, we take inspiration by the standard definition of phases that we have in condensed-matter, which is recalled here. So we have two states, and these two states are in the same phase if there is a quantum circuit of flow that connects them. But a more formal way to state this would be the following: that we say that two states are in the same phase if you can find a unitary circuit of depth, which is a function of the system size, such that the distance between the two goes to 0 as m goes to infinity. And now we can now put restrictions on this f, which should grow sufficiently slowly. So, for example, you could choose that it grows less than any real power, or maybe it's a polylogarithmic function. Okay, so now we try to adapt directly this definition to our case, but there are many subtleties, which are related to the fact that you want this to be a transitive transformation, sorry, a transitive relation. And so this is why we have to allow for small probabilities of failure. Namely, if we start from one state, we need to allow that we do not perfectly end up in a pure state, but we might end up in a mixed state. So the definition is this one. So first of all, we say that given a sequence of states, we can prepare a new one. We can approximate the new sequence of states if there exists a family of mixed states which is exactly realizable starting from your state with some, using this procedure, using a quantum circuit that scales sufficiently slowly with the system size. And then we simply say that two states are in the same phase if I can do this starting from either of the two states. And we have to force this symmetry by hand, because when it comes to measurement, it's not true that if I can go from one state to the other, the vice versa is true. Trivially, any state, I can measure all the sites, and this gives you the product state, but the converse obviously is not true. Okay, so using now, so this definition is a suggestion, so it might be that it has to be refined, and looking at examples, especially in higher dimension, is the good way to see whether this is too naive. But using this exact definition and sticking to one dimension, we arrive at one result, which is perhaps simple, but it's at least precise, which is that if we restrict to the class of matrix product states, then all matrix product states are in the same phase. And now let me explain this in a bit more detail. So matrix product states are a prototypical example of ground states of local Hamiltonian for one-dimensional systems. They're an example of, the simplest example of tensor network states. And this is the formal definition. But the point is that so here we're sticking to translation invariant system because it's what we want to define phases in the thermodynamic limit. And a known fact is that translation invariant states are always the ground state of some Hamiltonian, but for every state, we can attach to it a minimal degeneracy of the corresponding Hamiltonian. So, for example, product states are the unique ground state of some local Hamiltonian. If we take, for example, the GHZ state, this corresponds to the degeneracy 2. And so the standard classification of matrix product states without symmetries was done long ago by Norbert Schuck and collaborators. And essentially, it tells you that the degeneracy completely classifies the phases. So if I have the product state, I cannot prepare the GHZ state because the degeneracy is different.
Lorenzo, just a question. Yeah. So since you want to scale to thermodynamic limit, I mean, you mean a fixed bond dimension, like MPS?
So here, exactly.
We're also scale.
No, exactly. So here we're sticking to finite bond dimension, right. Yes. All right, so instead our result is that this sequence of phases all merge into a single one, which, I mean, it's what we would expect, that this new transformations are more powerful than before. And so this is the only slide to convey the idea. So the idea is that we start with some matrix product state, and for matrix product state, there is a rigorous notion of real space RG transformation. So the idea is you start with some matrix product state, and then you look at its fixed point representative. What you can do is to show that if you group together sufficiently many sites, then you can approximate this RG fixed point. And then what we do is to show explicitly a construction starting from the product state to realize this, this RG fixed point. So then this means that we're able to construct any matrix product state in this way. Okay, so this is for 1D. Now let me come to the outlook. Here, so this work mainly is about questions rather than answers, and one which is particularly natural is what happens to the classification in 2D. So there are some obvious generalization of what we do, but there are also some problems which look very hard, and one of them is to try to realize non-abelian topological order. So when we posted this, we thought this was very difficult, but then several people, many of which are in the audience, in fact realized example of non-abelian topological order. And so specifically restricted to some special class. So again, for the experts, I think the state of the art is that some models involving solvable non-abelian groups now can be realized, but it's still an open question, and probably the answer is no, whether arbitrary topological order can be realized in this way. Then, of course, there is another question which pertains to stability of this transformation with respect to noise. And again, here, some work in this direction has been done by Ruben and collaborators, and other people, again, in the audience, have touched upon this issue, but I think this is still very much open in general. And then finally, again, speculation level, I think it could be interesting to think about applications out of equilibrium. For example, something which is fairly natural is to try to think about a kind of deterministic evolution where we need to, it's essentially adaptive measurement dynamics, but then it would be interesting to understand whether these kinds of dynamics can host new or non-trivial phase transitions, which would give rise to some post-selection free, maybe non-trivial, measurement-based transition. Okay, so this is the last slide, so I thank you for your attention.
Questions, please. Yes, please.
Thanks for your talk. I actually have plenty of questions, so I'll just ask a few of them
go ahead.
Before passing the mic on. So the first one is, for your claim 1, I mean, it already followed from previous results. Like, did you need to prove anything else beyond that, or no?
So you mean that you couldn't create a new state?
Yeah. Right.
No, I mean, so this was, again, this was known somehow. The GC state, that has been known forever.
Yeah.
Topological probably, no. So the only thing we did was to, formalize because, I mean, if you, for example, allow arbitrary number of ancillas, then you can do anything. So this was the setup part of the work to
okay.
Construct the protocol and then start to see, okay, what do we know, and then maybe what don't we know?
Yeah. Okay. And at some point you emphasized that it's important to pay attention about the transformation both ways. Right. So in your 1D MPS classification, I didn't understand this step where you show that you can make the RG fixed point from a product state, but then how do you go back to the state phi that it flowed from? Right.
So I mean the MPS case is a bit trivial because there is a single class. So really the only hard part is to show that you give me a product state, I can construct an MPS, because the other is always trivial. So you give me an MPS, I measure all the sites, I correct locally to get the 0, 0, 0. So the two states are clearly connected.
No, I mean, how do you go from the RG fixed point back to the initial state that you started flowing from, which may not have anything to do with product state?
I mean,
right?
If you want, you can pass. I mean, you pass from the. So we know product state. We know to arrive at the fixed point. So anything that is connected to the trivial product state, we can always get to, right? Because we first arrive at the product state.
I guess I mean to ask whether the RG flow itself is reversible.
Sorry, maybe because maybe I didn't emphasize this, but when you define this class of, I realize I didn't emphasize this. When you define this classification, you need to be able to apply this protocol a finite number of times, right? So because otherwise you don't necessarily have transitivity. So I go from A to B, and then so if you start from some MPS, what you would do is you go to the trivial state, and then you know how to go from the trivial state to the fixed point. So all the three layers are connected somehow.
Okay.
This was your question.
Yeah.
Okay.
Other questions?
You said it had been known for a while how to classify states that are equivalent up to LOCCs, and then you added this quantum circuit plus LOCC. So can you comment on what LOCCs alone get us and what the quantum circuit adds? And then also if you take away the classical communication and you only have quantum circuit plus local operations, and how that differs?
Okay. So first of all, LOCC alone are very weak. As far as I know, so for sure, okay, there are many things which are not known. There is a full classification when you have just two parties. This is all work. But when you have a many body system, I think what it's known is that most of the states are disconnected. So if you sit on a state and you only have a LOCC, you can get essentially, you cannot reach any other state with, probability 1. So at least, quantum circuits allows you to probably, at least, so because the point is LOCC do not create entanglement. So quantum circuit allows you to create entanglement. Okay, so these are two questions, and then the third one was, sorry.
If you remove the CC.
Yeah, this is a very good question. So my guess is that probably, unless you really have trivial protocols, you will not be able to realize everything you will realize, it will be non-deterministic. You will not be able to remove, say, the random part of the protocol. That's my guess. But you will still be able to generate long-range order and long-range entanglement. I see another question there.
So I guess a different type of transformation I could consider is something like a finite depth circuit of quantum channels instead of unitaries. Yes. Instead of combining unitary circuits with LOCC.
But a very special type of channel.
Well, my question is, if I consider the general case of finite depth circuit made out of channels, how does that relate to the type of thing you consider?
Yeah, so this is a very good question. Right, okay, so some statements carry through. So if whatever channel you have, this is a deterministic transformation, then you will still have an error-low entanglement. The problem, so again, LOCC is this very special class of quantum channels. And in fact, it's a mathematically extremely difficult problem to characterize exactly the form of this LOCC. This is a very well-known problem in quantum information. So I guess, it's a very hard question probably to understand how the phases change if you change the channel. Probably will be, it will be channel dependent somehow, but this is a very difficult question. I don't know how to answer now.
So,
I see another question here.
Thank you for the really nice talk. Maybe just an outlook question. I know that you can take LOCC and expand its power and capability and the states you can reach if you begin to also combine some other ideas with it, like these quasi-distributions. For instance, you can begin to teleport C-naughts and do entangling operations with the LOCCs. I just wonder whether you've thought about some of that.
Right, so no, we have not considered this. This is a very good question, but we haven't considered this. I guess another natural direction, which again was probably touched upon in one of the subsequent works, is what happens when you allow for a little exponential tail. So you don't take quantum circuit, but maybe actual Hamiltonian dynamics. But this is something we haven't explored. So, but certainly it's something which is interesting to consider for future work. I see a question over there.
Thank you. So maybe a follow-up on Vedika's question. If you don't have CC, just local operations,
right.
I guess you could still create invertible states, or basically maybe a simple example, you could probably still enact translation as a map.
But sorry, but then you mean deterministically or?
Deterministically, because you would just end up, say, measuring one, like, or maybe thinking of an invertible state, something you can get with LU.
Right.
But you can create double copy with LU, and then use measurement to remove one copy. But then since you don't care...
But then I guess, I mean, if you want an invertible state, you don't even need probably measurements, right? You take two copies, you construct, because, I mean, if you take two copies together, this is a quantum circuit suffices, and then you simply separate the two, right?
Right. Is that LO? Does it count as LO? Just maybe removing a layer? Maybe that's a question. Like, does LO?
Oh, okay. No. This is a very good. Okay, sorry. Okay, no. This is a very good question. So the question I think you can rephrase as: I only have quantum circuit on one end, and the other I have quantum circuits plus ancillas. So without measurements. And yeah, okay. So first of all, this makes a difference in the kind of unitary operations that you can prepare. For example, the shift you mentioned. And I guess, yeah, probably invertible order tells you also that even only having ancillas buys you something that you couldn't do without circuits. Yeah.
Thank you.
Thank you.
So sorry, what you did?
Tyrone, can you unmute yourself?
Thank you. Yeah, a great talk. So I have a question about restrictions on how complex a state can you get, and more precisely, but are there any constraints on the circuit complexity of? So you allow measurements, and I mean, you do LOCC and unitaries, and you get some state. And let's say then I ask, if I had only access to unitaries, how deep a circuit I need to prepare that? Is there any constraint? Because you mentioned, for example, constraint on the entanglement. For example, you can only generate area law states. Are there constraints on the complexity, circuit complexity?
Okay, so thank you. So I guess the problem is that usually complexity, at least, I mean, in the recent literature, they talk about complexity linear versus exponential scaling, right? Mm-hmm. But here, I mean, really order one versus linear. So somehow, I mean, everything we prepare, I guess, because you're okay. I mean, okay. So in higher dimension, I don't know, but since you cannot prepare volume law, I would say that anything you prepare is probably going to be not complex in the way that. You know, complex states are defined recently where you need an exponentially deep quantum circuit to prepare. So I mean, this is my guess that you cannot prepare complex states in the technical sense.
And you can prove that I guess is that obvious that you can't prepare exponentially complex states?
So I'm sure there are experts in the audience who could answer right away. One dimension, I think it's obvious. In a higher dimension, it looks very reasonable. So the question is, okay, I prepare an area law state. Can I rule out that I need an exponentially deep circuit to do that? I would say so, but I don't know whether someone has a on the fly elementary proof for that. But this is a good question.
Thank you.
Yeah. Okay, so maybe one more last question, yes.
You mentioned some really nice follow-up work where they prepare other kinds of states.
Sorry, they prepare, sorry?
Where they prepare other kinds of states in this other nice follow-up works.
Yeah.
But yeah, is there any improvement on what classes of unitaries you can implement with this?
Thank you, good question. Yeah, so this is one of the parts of the work that hasn't, to my knowledge, hasn't been touched upon. So no, I would say no. What we think, I mean, maybe if you restrict to our protocol, maybe you could prove that you could only do some area law stabilizer, sorry, Clifford operation. But no, yeah, this hasn't been expanded upon.
Do you have like a speculation one way or another, whether, you know, there's like a much larger class of unitaries?
I mean, my expectation is that you cannot do much better than this. But again, I was surprised, for example, that they could realize non-abelian topological order. So maybe if you're creative enough, maybe you can find a slightly different protocol.
Thanks.
Yeah.
Okay, so let's thank Lorenzo again.